First, we'll look at the layers of the atmosphere based on composition. Here's another one of the International Space Station images showcasing the layers of the atmosphere. If we look at the top, it's very difficult to discern or tell where our upper atmosphere ends and where outer space begins. It's a very long transition zone. So when we look at the layers of the atmosphere, we're going to work our way from the top and work our way down. This is an image that we'll be working with on the following video lectures. And I highly suggest being able to maybe draw this or at least conceptually understand where one specific layer begins, another one ends. And just so we know, all know what we're looking at on the left-hand side, from the bottom all the way up to the top, from 0 to 300, that's reference miles above sea level. And so sea level would be 0. On the right-hand side, you should see this grayish-white looking triangle. That's Mount Everest, the tallest location or the highest point you can find anywhere on land. So that's the highest elevated area on Earth. If we look at the top, the exosphere, that's the first layer that we're going to look at. It's really not even a layer. An exosphere, just think of it as outer space. And so outer space begins roughly about 300 miles above Earth's surface. But that's big, huge, roughly. We'll talk about that on the following slide. The exosphere is 300 to 6,000 miles above Earth's surface. And so once again, it's a very large transition from the top of our atmosphere to outer space. And so the exosphere, the closer you get to that 300 miles, you're going to find a sparse field of hydrogen and helium atoms. So essentially outer space is just mostly hydrogen atoms that are spread out quite far from each other. If we think about the black space, and I'm not going to go too much into outer space here as far as the mechanics of it. But as far as you get closer to the exosphere, you're going to find a little bit more helium presence there. The idea here is the exosphere, the further you are from Earth, you're going to be affected less by its gravitational pull. And so these hydrogen and helium atoms are very loosely bound to Earth, or kind of loosely held close to that 300-mile level due to Earth's gravitational pull. So this area very much slowly thins while blending into space. And it's essentially a vacuum, outer space, a vacuum of just mostly low-density hydrogen atoms. Next up, we're going to look at the heterosphere. And if you look over here on the right-hand side, you can see these overlaps between these different types of spheres, these different layers. And so, once again, we're just focusing in on composition. So, homosphere and heterosphere both relate to composition. Troposphere, stratosphere, mesosphere, thermosphere all relate to temperature. And ozonosphere and ionosphere relate to function. And once again, we're focusing just on composition, so we're going to be looking at heterosphere and homosphere. And so the heterosphere we find at the top level of our atmosphere, so from 50 to 300 miles above Earth's surface. The heterosphere is also referred to as Earth's outer atmosphere. Here, what we would find composition-wise is a specific pattern in which gases, they're not evenly mixed. And so what we'd find is the composition of the heterosphere varies with altitude. In the homosphere, there is none of that composition varying with altitude. However, in the heterosphere, we find these distinct layers distinguishing one from the other. Key to understanding these layers are that the gases are sorted by gravity and atomic mass. So if we look at the layers, we'd find the heavier ones, the ones with the greater atomic mass, are found at the bottom of the heterosphere, where the lighter ones are found at the top of the heterosphere. And we'd find this distinctive pattern of hydrogen and helium at the outer edge. Keep in mind, go back to the exosphere, look what we'd find in the exosphere, and so that kind of makes sense. And so hydrogen and helium, they have a lower atomic mass. They don't weigh as much as you would find for the nitrogen and oxygen. So we'd find these distinctive layers. You'd find hydrogen, then helium, then nitrogen, then oxygen, these distinctive layers as you go from the top down in the heterosphere. So let's try to figure out, okay, why do we find these layers? And so hydrogen is the lightest. If you look at the top left, hydrogen, the atomic mass is that number below the H. Compare that to He. On the top right-hand corner, He has an atomic mass of about 4. Then we go to nitrogen. We find that also over on the top right, N, and it has 14.007 underneath that. And then next to it is oxygen. So we could think of the hydrogen atomic mass being 1, helium 4, nitrogen 14, oxygen 16, and so that makes sense based on what we saw on the previous slide, that we're going to find these distinctive layers with the lightest one at the top, the heaviest one at the bottom. In our orbiting satellites, most of the satellites that are orbiting Earth are found in the heterosphere, up in this upper level of the atmosphere. And this is a crude visual, but this showcases, once again, the hydrogen, helium, nitrogen, oxygen, the distinctive layers that one would find in the heterosphere. Next up is the homosphere, which is obviously going to be below the heterosphere. Next up is the homosphere, also referred to as Earth's inner atmosphere, from 0 to 50 miles above Earth's surface. And so unlike the heterosphere, here gases are evenly mixed. And so if I went out and I cupped the air, if I got a sample of the air, I wouldn't find any distinctive layers. It would be a fairly even, uniform mix of gases. So it's a very uniform, constant composition. There are some exceptions. We'll come back and we'll talk about the ozone layer in a minute when we talk about the ozonosphere. But in the ozone layer, you do see areas that have higher concentrations of O3, which we'll talk about here in a minute, than other areas further below the ozone layer. Also, you're going to find variations in water vapor, i.e. clouds, CO2 or carbon dioxide, pollutants. You're going to find variations. And so, of course, cities are going to have higher CO2 levels, higher pollutant levels than rural areas, because there's more cars in those areas, there's more stuff going on in those areas. So, of course, if I sampled the air, it would be different than the air I would sample in a rural area. Same with water vapor. Water vapor, we find a huge amount of water vapor in the tropics, where think of water vapor as rain or clouds. And so, of course, there I'm going to have a variation compared to the desert areas. But for the most part, in the homosphere, the key thing that distinguishes it from the heterosphere is the fact that gases are evenly mixed. Two largest components of our homosphere are nitrogen and oxygen. So our atmosphere is overwhelmingly nitrogen and oxygen, and from there, argon, carbon dioxide, and a motley mix of others. The composition of our homosphere is overwhelmingly nitrogen at 78%, and that nitrogen likely came from the many volcanic eruptions that have been occurring on Earth for the 4.54 billion years Earth has been around. And this is very important to the nitrogen cycle, which we will discuss later in the semester. Number 2 is oxygen at 21%, and that oxygen is a byproduct, or it comes from photosynthesis. Oxygen also forms compounds that comprise 1/2 of Earth's crust, and so we also find a good amount of oxygen not only in the atmosphere but also in the Earth's crust. And of course, oxygen is important for biological activities, very important for humans and our breathing, obviously. Third would be argon at 1%. Argon is an inert gas. Inert gas meaning it's unreactive, or it's also a noble gas. And so essentially it's unusable in life processes. And our body does not use argon and does not need argon. However, what's interesting is argon, which is found in the atmosphere, is actually being mined. It's being mined for industrial purposes. And so some of you who work in welding or work with lasers actually use argon. So it's something that's kind of interesting. We often think of things that are being mined as things being in the ground, i.e. coal. However, you can also mine specific gases from our atmosphere, and that's been done. Next up would be carbon dioxide. Carbon dioxide, obviously much less than 1%, but very important greenhouse gas. I'll come back in a few video lectures from now, talk about what a greenhouse gas is. One thing is carbon dioxide, it is increasing. And so whether or not you're for global warming or against it, there's no doubt that the levels currently of carbon dioxide are increasing. Two key reasons for that are the burning of fossil fuels, which add carbon dioxide to the atmosphere, but also deforestation. Deforestation, if we think about trees, what they do is they take in carbon dioxide and release oxygen, i.e. photosynthesis, and so if there's less trees around, you're going to see less of that intake of carbon dioxide. Next up is water vapor. Water vapor, just pretty much think of it as clouds. Especially in the lower hemisphere, we're going to find more quantities of water vapor than the upper levels of the hemisphere, especially between the tropics. And so if you look at a world map, a real-time map of water vapor on Earth, you're going to see a huge amount there in between the tropics. And water vapor is another greenhouse gas, and I'll come back in a future video lecture and once again explain what a greenhouse gas is. Next up is ozone. And so ozone is a specific situation we find at the top of the Ozonosphere. And so we'll come back and talk about ozone in a future video lecture that looks at the function of our atmosphere.